Let's find the excited energy eigenstates of the quantum harmonic oscillator in the position representation. In the previous few videos of the quantum mechanics playlist, I have found the ground state wave function in the position representation. I've also normalized that wave function, so I found the normalization coefficient. In this video, I'm going to use the raising operator to act on that ground state, and that's going to give me the excited states. And we're going to find some very interesting relationships that are present in the excited wave functions of the quantum harmonic oscillator. First, I'm going to write down the raising operator. So the raising operator, a hat with a dagger, is equal to the square root of m omega over 2h bar. That's just a coefficient out the front. Then we have the position operator minus I over m omega times the momentum operator. So here we have position, and here we have momentum. And it's important to note that there is a minus sign over here. And this minus sign comes from taking the Hermitian adjoint. So a dagger is the Hermitian adjoint of A. And A is also known as the lowering operator. And when we take the Hermitian adjoint, or the Hermitian conjugate of the lowering operator, we get the raising operator. There are plenty of videos in the quantum mechanics playlist where I go over the algebra of these ladder operators. Collectively, they're known as the ladder operators, the raising and lowering operators. So in the derivation for the ground state wave function, I used the lowering operator. I acted with the lowering operator on the ground state, and that gave me 0. And from that, I wrote that in the position representation, and that gave me a differential equation to solve. I solved that differential equation, and I found a Gaussian function. And then I normalized that Gaussian function. Another important thing that I want to write down over here is that any energy eigenstate labeled by n, so this is Dirac notation, we have a ket, that can be written as a dagger, the raising operator, acting n times on the ground state ket. But we have to divide by this factor of square root of n factorial. And that is just to maintain normalization. So we always need to preserve normalization. Normalization is a very important condition because it allows us to get meaningful probabilities. And that is what the goal of all of this quantum mechanics formalism is. We want to get probabilities, we want to get expectation values and variances. We want to predict experimental measurements. So that's why I'm very meticulous about normalization. So this n over here, this lowercase n, that is an eigenvalue of the number operator. And it labels this ket. So this is the nth eigenstate, energy eigenstate of the quantum harmonic oscillator. And you can get that from the ground state. All you have to do is apply the raising operator to the ground state n times, and that will get you up to the nth state. I also derived this relationship in a previous video. And finally, what I want to write is the form of the ground state wave function, labeled by psi sub 0, also known as psi naught. This depends on x because we're in the position representation. The normalization coefficient is m omega over pi h bar, and that is to the power of a quarter. And in the previous video, we saw why this is to the power of a quarter, because we already had a square root, and then we have to square root it again. So a square root is the same as raising this coefficient to the power of a half, and then we have a half times a half by exponent laws, and that gives us a quarter. So that's the normalization coefficient, and then we have the Gaussian function, which is e to the minus m omega over 2 h bar x squared. So what I'm going to do is I'm going to apply this formula in the position representation, and I need this in the position representation. Another thing that I want to stress on is that we're going to see this combination and this combination appearing again and again in this derivation. So it's important to make the distinction that over here we have a 2 and over here we have a pi. These are not the same coefficients. Here we have a pi, and that comes from the Gaussian integral, and this is a 2 over here. That comes from solving the differential equation in some of the previous videos where we were defining and deriving the ground state wave function. So what I want to do is I want to write a general expression in the position basis. So this general expression is going to be for psi n. So I'm going to have psi n over here. So psi 0 is the ground state. And this psi n should work for any eigenfunction. So as long as it's an energy eigenfunction, it should fit this form over here. So what do I need over here? What I need is this form in the position representation. So I'm going to take this equation over here and write it in the position representation. And I'm going to have to take this ladder operator, this raising operator, I'm going to have to take all of these guys and write them in their position representations. So this is going to be equal to, I need this 1 over square root of n factorial. I'm going to keep track of all the normalization coefficients. It is a bit tedious, but I think it's worth it because you want to see where all those normalization coefficients are coming from. You don't want to just have a random coefficient out the front and not know where it came from. So this is just coming from here. We have 1 over the square root of n factorial. Now, let's get this guy in the position representation. What I'm going to do is I'm going to bring this coefficient inside because it's going to allow us to cancel some terms out. So inside here, I'm going to have the square root of m omega over 2h bar times the position operator in the position representation, that's just multiplying by x, minus, we're going to have this guy again, square root of m omega over 2h bar, and then we have I times m omega. And what is momentum in the position representation? Well, momentum is the same as differentiating with a constant out the front. And that constant is h bar over I. You can also write h bar over I as minus I h bar. That's because minus I is the same as dividing by I. So negating I is the same as the reciprocal of I. And what we have is a derivative with respect to x. And I'm going to write a total derivative over here, but in general, it's better to write a partial derivative in general. But because we're just dealing with functions of x over here, there's actually no time dependence that's going to show up over here because these are actually stationary states. I'm just going to write this total derivative, so d dx. If we're dealing with higher dimensions and we have x, y, and z, or we have to differentiate with respect to time, then I will specifically write partial derivative with respect to x. But over here, I think it's fine to just write the total derivative. And let me close this off with a little bracket and raise this to the power of n. So we have n copies of this. And then I want to act on the ground state wave function. So this line over here is equal to this blue formula. It's the same as this blue formula. But the only difference is I've taken the position representation. The position representation of the nth energy eigenstate, that is this wave function labeled by psi sub n. So this wave function, that is the position representation of this guy. And this combination of the raising operator acting n times and then being divided by the square root of n factorial, that is all of this mess. And then the position representation of the ground state is psi naught. So that's this ground state wave function in the position representation. And it's important to remember that we're applying this combination n times. That is this raising operator n times. So let's have a look at all of this mess inside. So I've moved this coefficient inside over here, and that's multiplying the x. That's x in the position representation. And then momentum in the position representation, that is this combination, h bar and I d dx, right? This derivative. And all of these guys over here, we have this coefficient times this coefficient. Can you see that all of this is actually going to simplify a great deal? We have I and I over here. I divided by I, those i's are going to cancel. It's the same if we wrote this as minus I, because I times minus I, that's plus 1. So that's going to disappear. We also have an h bar over m omega appearing outside. And then we have the reciprocal of that appearing inside over here. We have m omega over h bar. So when we move this guy inside, what we're actually going to get is the reciprocal of what this is on the inside. We're going to have a coefficient that is the reciprocal. Another thing I want you to notice is that there is a square root of 2 over here and a square root of 2. We're dividing by square root of 2. So we can actually pull that common factor of square root of 2 outside. And that's going to give us square root of 2 to the n, because we're applying this n times. So I'm going to group this together into one big normalization coefficient. I'm also going to take this normalization coefficient from the eigenfunction over here, from the ground state eigenfunction. So that's going to give me m omega over 2h bar. Actually, that's pi h bar. I have to remember that we have a pi over here and a 2 up there. I'm just very used to writing 2 because it appears in this combination very frequently. It appears over here and over here. So this is specifically a pi h bar. So we have pi h bar down here, and that's to the power of a quarter. And then we're going to have to divide by, we have n factorial under the square root, and we also have 2 to the n, because this is n times. So we're going to have square root of 2 to the n factorial. What a messy coefficient out the front. But it is this messy coefficient that's going to help us make sure that normalization is preserved. So this factor, m omega over pi h bar to the power of a quarter, that comes from this ground state wave function. And this factor of the square root of 2 to the n times n factorial, that comes from applying the raising operator n times. So that is the normalization coefficient, which I've just moved out to the front. Now let's have a look at what happens to all these brackets over here. So we're going to have n copies of this, and I've moved this 2 out, so I don't need to write the 2 anymore. We're just going to have square root of m omega over h bar times x. And what are we going to have over here? We're going to have a minus sign. So we're still going to have a minus sign. But now, because these i's have disappeared, and if we move this h bar of m omega inside, that's going to give us the reciprocal on the inside. So we're going to have h bar on m omega. That's what's inside. And we're still going to have this derivative. So the imaginary unit I has disappeared. We don't have it here anymore. And we have to apply this n times to this Gaussian function, m omega over 2h bar x squared. That's m omega over 2h bar x squared. We have a 2 appearing over here, and we have a pi appearing over here. So what has happened over here? This has simplified a great deal. We have m omega over h bar appearing underneath this square root, and over here we have the reciprocal of that. And the reason we have a reciprocal is because h bar over m omega appears on the outside, and m omega over h bar appears on the inside. So this is actually the square of this. So that's why we get the reciprocal. And another way to look at this is these coefficients ensure that the units work out. There is dimensional consistency. Position and momentum don't have the same units. That's why they always have different coefficients out the front in these equations, because we want to make sure that the dimensions of the problem are consistent. So all the normalization coefficients have been grouped out over here. We have n copies of this operator acting on the Gaussian function. I've split this wave function into 2 parts. We have this guy over here and this Gaussian coefficient. So this coefficient and this guy were together in this ground state wave function. This, in general, gives you all of the energy eigenfunctions. Let's find the first 2 excited states. So we're going to do that underneath. We're going to find the first 2 excited states. First, let's set n equal to 1. So if we set n equal to 1, we're going to get the first excited state. If n was equal to 0, we would just get this. We already know what that is. This is n equal to 0. If I set n equal to 0 over here, 0 factorial is 1. 2 to the power of 0, that's also 1. So this disappears. N equal to 0 over here, that means we don't apply this at all. We apply this 0 times. So this disappears, and then we're just left with this coefficient times this over here. And that's exactly what we have up here. That is the ground state wave function. But now let's set n equal to 1. If we set n equal to 1, we have 2 to the power of 1, that's 2, times 1 factorial. 1 factorial is 1. So we're just going to have this coefficient divided by the square root of 2. So I'm going to write that over here. M omega over pi h bar, not 2 h bar, pi h bar, to the power of a quarter over the square root of 2. And now what I want to do is I want to apply this combination once, because n is equal to 1 for the first excited state. I'm going to apply all of this to the Gaussian. Now what is that going to look like? Immediately, I'm just going to bring this inside here. So I'm going to apply this, and then I'm going to apply this derivative. So first, what is this going to look like? We're just multiplying by x. In the position representation, applying the position operator is the same as multiplying by x. So I'm still going to have this coefficient, square root of m omega over h bar. Then I'm going to multiply by x. And that's going to give me x times e to the minus m omega over 2h bar x squared. So that's what I get from this position operator term. Now let's have a look at this derivative. What happens when I act with the derivative? I'm going to have a minus sign, and that minus sign is then going to be followed by this coefficient of h bar over m omega. So that's still working out. So I still have this minus sign. But then when I take the derivative, I'm going to have to use the chain rule. So using the chain rule, that's going to give me the derivative of this quadratic over here. So we actually have x squared on 2. The derivative of x squared on 2 is just equal to x. So when I use the chain rule, I'm going to get an extra factor of x. But I'm also going to get this coefficient of minus m omega on h bar. And that minus sign is going to get rid of this minus sign over here. So I'm going to have a plus sign. So I'm going to have plus m omega over h bar. So that's just this coefficient over here. The 2 has disappeared when we take the derivative in the chain rule. So we're just left with x, and then we have, again, e to the minus m omega over 2 h bar x squared. And I'll close this bracket over here. So I'm closing that bracket, and let's have a look at what we've got. So this has come from multiplying by x, and this over here has come from multiplying by this coefficient. We have the reciprocal of this guy, and then we have taking the derivative. So we're just taking the derivative. When we take the derivative, all we have to do is take the derivative of this guy in the top, because the derivative of an exponential is just the exponential itself. And then we use the chain rule. We differentiate this quadratic function. That gives us a linear function. And this linear function, x, has a coefficient m omega over h bar with a minus sign. But we already had a minus sign over here. This minus sign cancels with that minus sign. Another thing I want you to notice is that when we take this guy and we multiply it, we can simplify it, and that's going to give this coefficient. By the same reasoning that we had over here, you have the reciprocal on the outside, and that's equal to the square of what's inside. So these guys together are going to combine to give square root of m omega over h bar. So we're going to have 2 copies of the same thing. So 2 copies of the exact same thing, and I'll write that in a more condensed form. We still have to write that normalization coefficient, that pesky normalization coefficient, which is actually going to help us make real-world predictions. M omega over pi h bar to the power of a quarter divided by square root of 2. So that's the normalization coefficient. And then I'm going to write this in a slightly peculiar way, but it's very suggestive as to a pattern we're going to see later. I'm going to write this as 2 copies, because we have 2 copies of this, 2 copies of the square root of m omega over h bar times x. So that's a linear polynomial. 2 copies of square root of m omega over h bar times x, and then we have the Gaussian. The Gaussian is always going to be there. M omega over 2h bar x squared. So this is the first excited wave function, psi sub 0. This corresponds to the first excited energy state. This guy has the ground state energy. It has h bar omega over 2. This guy has an extra unit of h bar omega. So this corresponds to 3 on 2 times h bar omega. So that's the energy eigenvalue associated with this energy eigenstate. We still have that same normalization coefficient. We just group these guys together. This guy also has a polynomial inside it, but that polynomial is just 1. But this guy has a linear polynomial over here. So we have 2 times this factor times x. Now I want to do one more just to illustrate a point. So I'm going to do one more of these guys, and let's do it in black. So we'll go psi sub 2 of x. That's what happens when we set n equal to 2. And we've actually done a lot of the work over here because we've already applied this operator to the Gaussian once. We just have to apply it again. So first, I'm going to move all the constants out so we don't have to worry about carrying all of these constants all over the place. So what is this going to be? Well, we're still going to have this m omega over pi h bar to the power of a quarter. And what are we going to have downstairs? Well, downstairs in the denominator, 2 to the power of 2, right, because we're dealing with n equals 2, that's 4. And 2 factorial is 2. So we're going to have 2 squared times 2, that's 8. So we're going to have the square root of 8. So you can see that there's a different value appearing in the square root for different energy eigenstates. That's why we have to specify that value. And that's why it's labeled by n. So that's what we have downstairs over here. That's just come from 2 squared times 2. That's square root of 8. So I'm going to leave that out the front. The next thing that I'm interested in is these coefficients over here. So what I'm going to have to do is I'm going to have to apply this to the Gaussian twice. But this result over here, this has come from acting with this combination on the Gaussian already. So we have one copy of that. Now we just have to take this operator and act on this x times the Gaussian. I can actually ignore these guys because they're just real coefficients. I can move those guys around. They obey commutativity. They're just real numbers. So I'm going to write 2 times all of this mess out the front over here. So I'm going to have 2 times the square root of m omega over h bar. So that's what I have over here. 2 times the square root of m omega over h bar. And this x over here, I can't move that. I'm not allowed to move that because this is not a real number. I need to have this operator acting on x times the Gaussian. So what's that going to give me? It's actually going to be a little bit complicated because we're going to have to use some differentiation laws. We're going to have to use the product rule as well. So what I want you to notice is that all of these guys, all of these coefficients have been moved to the left. So over here we have a square root of 8 now because we're dealing with n equals 2. Now what I want to do is I want to apply this combination of x and this derivative with respect to x to x times the Gaussian. So just consider this. I'm applying this combination to this one more time because I've already applied it once. So what's going to happen when x acts on this combination? Well, we're just going to get this guy over here, square root of m omega over h bar times x. We already have an x. That's going to give an x squared. So you might already see we're going to see a quadratic polynomial emerging. And we always have this Gaussian with us. That Gaussian is not going to escape quite yet. So we have m omega over 2h bar times x squared over here. That has come from this term. That's what happens when we act with this combination on x times the Gaussian. So we just get an x squared appearing outside the Gaussian. And this square root of m omega over h bar, that coefficient over here is actually the same one that we factored out. So that's going to become important in a second. Now what we want to do is we want to act with this combination on x times the Gaussian. So we're going to have minus the square root of h bar over m omega. That's this guy over here. And then we're going to have to take the derivative. And the derivative is going to have two terms because we're going to have to use the product rule. We have a product of two functions. First, I'm going to differentiate with respect to this Gaussian. I'm going to take this Gaussian, I'm going to differentiate it, I'm going to leave x alone. If I leave x alone, we're going to have the same trick that we used over here to perform the derivative. So we're going to have this combination, the derivative of all of this, emerging outside. So we're going to have minus m omega over h bar. That 2 is going to disappear when we differentiate because we have x squared on 2. That's going to give x. So we're going to have x over here, but we already have an x. So we're going to have x times x. That's x squared. And e to the minus m omega over 2 h bar x squared is also here. So that's that Gaussian. Now let's leave this guy alone and differentiate x. The derivative of x is just equal to 1. So now we can just add the Gaussian by itself because this guy's been differentiated and it's just turned into 1. So we have e to the minus m omega over 2 h bar x squared. And I'll close this bracket. That's the bracket corresponding to the derivative. And then we have another bracket. I'll close that bracket over here. So we have a bit of a bracket mess. So all the coefficients are at the front. Here we have this one set of brackets. This is what happens when we act with this x operator over here. And this big mess over here is what happens when we act with the derivative operator. Now let's group some terms together. I'll write that underneath. We're going to group these terms together. That's going to give us a simple expression. So let me write this normalization coefficient of m omega over pi h bar to the power of 4. I'm going to keep this as square root of 8 so we can see the pattern. Then I want you to notice that the Gaussian appears in all of these terms. So I can factor that Gaussian. I'm going to move it out to the right. I want to keep it in this form over here. So I'm going to have a polynomial times a Gaussian. That's going to be the result. So if you notice over here, we have an x squared, and over here we have an x squared. So we can group those two terms together. What's going to happen over here? Here we have a 2, and then we have 2 copies of the square root of m omega over h bar. So that's what's multiplying this guy. What about for this x squared times the Gaussian? Here we have m omega over h bar. That's the reciprocal of what's inside over here. So when we combine these guys together, these two minuses are going to give a plus. That minus sign is going to disappear. And then we're going to get the same coefficient over here. So we're going to have 2 copies of the same thing. And then we have 2 copies of the same thing multiplied by this coefficient. That's going to give us 4 times that coefficient. And I'm going to write that in a very suggestive form. I'm going to have 4 times the square root of m omega over h bar times x, all of that squared. So this is a bit of an unusual way to write it. I'm writing the square root times x all squared. Why not just write it without the square root? And why not just have x squared over here? Well, that's because this combination is showing up repeatedly. And you'll see in a second, once I finish this line. So we've got all the stuff that has x squared in it. We have this term and this term. We notice that taking the reciprocal, that just gives the same coefficient out the front. So that is what we've collected from these 2 terms. And we have one more term to deal with. This guy does not have a minus, so the 2 minus signs will not cancel. we're just going to have minus times the Gaussian by itself. But this guy does have this coefficient multiplying it. So when we distribute, this coefficient will multiply over here. And this coefficient is the reciprocal of this coefficient. You can see m omega over h bar and then h bar over m omega. So it's the reciprocal, and they're both underneath the square root. So when we multiply them together, we're just going to get 1. And then we're going to have 1 times 2. That factor of 2 is still there. So we're going to have minus 2. That minus sign comes from here. And this is the polynomial that I'm interested in. And remember, we factored out that Gaussian. So that Gaussian is still here. We have m omega over 2 h bar x squared. Now, let's notice what we have over here. We have a polynomial. Now it's quadratic. This guy was linear, and over here we had a constant polynomial. These polynomials actually have a very special name. They're called the Hermite polynomials. So I'm going to write something very important over here. I'm going to write a slightly different variable. So let's define the variable xi. This is the Greek letter xi. I'm going to define that variable to be equal to the square root of m omega over h bar times x. So this is essentially x with a scaling factor at the front. So this just makes sure that all the units work out. And this simplifies a lot of the equations. So you can see that m omega over h bar times x squared, that is just the square of this combination over here. So we can rewrite this in general. We can, in general, write any of these eigenfunctions, psi sub n of x. We can write them as some normalization coefficient, which is equal to this. So I'm not going to write this mess again, but it's equal to this, a sub n, and it depends on n because of the 2 to the n and the n factorial, times some Hermite polynomial, which also depends on n, and that's a function of xi. It's a function of this combination, square root of m omega over h bar times x. And then we have this Gaussian. And this Gaussian I can also write in terms of xi. I can write that as xi squared over 2. You can see if you square this over here, you're just going to get m omega over h bar times x squared. So the square root will disappear, and we'll have an x squared. And that's exactly what we see over here with a factor of 2. We're dividing by 2. So this is a Gaussian by itself, and this is a Hermite polynomial. I'll write that specifically underneath. This guy is a Hermite polynomial. Hermite polynomial. And Hermite was a very important mathematician, and that's actually where the Hermitian adjoint comes from. That name, Hermite, is in Hermitian. So we have polynomial. And these are a set of polynomials with very important properties, and they're used by mathematicians and statisticians, and especially by physicists. So let me write out some of the Hermite polynomials. The first one, corresponding to n equals 0, so h0 of xi, is just equal to 1. So that's what we saw in the ground state. In the first excited state, we have n equals 1 of xi, and that is equal to 2 times xi. And that's what we see over here. We have 2 times this variable xi. And the final one that I'm going to write in this video is h2. This corresponds to n equals 2 of xi, and that's equal to 4 xi squared minus 2. And that's what we got over here. So 4 xi squared minus 2. Where did we get this? We got this from combining all these terms from these differentiation laws. So we got this from the product rule over here and the chain rule. And that together it gave us these polynomials over here. These are the Hermite polynomials. And this guy we know is the Gaussian. And Gauss was another mathematician. So you can see the names of all these mathematicians appearing in all of these functions that we are naming in this video. So what did I actually do in this video? I used the raising operator, and I combined that with our understanding of the ground state wave function in the position representation. And I also used this relationship over here. I wrote that in the position representation. And I found this general form. This is a general form that tells you any energy eigenfunction of the quantum harmonic oscillator. If you know what value of n it is, you just have to substitute that value of n over here, and you can find any energy eigenfunction. Then in blue over here, I found the value that corresponds to n equals 1. So n equals 1 gives us this. This is the first excited state. So it's not the ground state, it is the first excited state. So we have one extra quanta of energy associated with this guy. One extra h bar omega. That's the quantum of energy in quantum mechanics, especially for the quantum harmonic oscillator. So this guy in black over here is the second excited state. And you can see it's got a quadratic polynomial multiplying it. So every time we take this combination of operators, this x and this derivative with these coefficients at the front, this minus sign ensures that we're going to keep getting these polynomials. And the beauty of this exponential function is that if you keep differentiating the exponential function, you're just going to get the exponential function times derivatives of what is being exponentiated. That's via the chain rule. And that's why the exponential function has such useful properties. So we're always going to have a polynomial times a Gaussian for all of these energy eigenfunctions. And these guys are stationary states. If you prepare the quantum harmonic oscillator system in one of these eigenfunctions, they will just stay in one of those eigenfunctions. Another thing I want to stress on is that these polynomials determine how many nodes are present in the wave function. So this ground state wave function is a simple bump. It only has one bump. Then when you multiply it by a linear function, that's going to turn it into an odd function. It's going to have two bumps like this. And then when you multiply by a quadratic function, it's going to go back to being even. And it's going to alternate between being even, odd, even, odd, even, odd, as you increase n. So it starts off as even, then it goes to odd, then even, then odd, and so on. So that is a very important property. And that actually comes from commutation relations between the parity operator and the Hamiltonian of the quantum harmonic oscillator. So everything really can be traced back to these fundamental commutation relations. They're actually where we can derive most of these expressions from. All this stuff has actually come from the algebra of commutators. So that is a very important point to stress on. So these guys all have physical graphs. And the more energy quanta you add to the system, the more nodes you're going to have. So that's an important thing to remember. The nodes are affected by this number n. And when you then take the square amplitude of all of those functions, that's going to give you the probability density functions. Okay, so let's finish this video. Make sure to find other videos in the quantum mechanics playlist. We will also do some other interesting derivations. You can find those videos if you click over here.